Swayam Prabha. Digital India. Educated India.
Hello friends, we are back with the fourth module of our MOOCs course on the topic of fundamentals of nuclear power generation. We already had 3 lectures on the topic of chain reaction in reactors, and today we are going to finish up this particular module by getting some more mathematical analysis about the neutron distribution inside the core, and then some idea about how to design a reactor. Just as a brief recap, I would like to go back primarily to the third lecture. Here we are discussing or we started discussing in this module about the chain reactions, where you are introduced to the topic of neutron life cycle and multiplication factor. And so now you have clear idea what is the requirement of having a chain reaction, and accordingly how can we control this multiplication factor by controlling several of its components, so that we can ensure a critical reactor. Critical means where for every fission reactions only one of the product nucleus is allowed to participate in a subsequent fission. In the previous lecture, that is in the third lecture, we have discussed in detail about the neutron diffusion theory, where this particular diffusion equation was developed. I think it was in the second lecture only where we developed this particular equation, which basically states the balance of neutron inside the reactor or in a particular location. So, right hand side here represent the rate of change of neutron density, with this small v being the velocity of the neutron, and on the left hand side we have 3 terms, where this first term is diffusion of neutron, which is also related to the leakage of neutrons, and we generally get this form by relating the current density of neutron with the gradient via the Fick's law of diffusion. Then we have the rate of absorption, and finally some source term, where source can be of 2 types. It can be an external source of neutron, or it can be neutron production because of the fission, commonly thermal fission. In the last lecture, we focused on this particular equation, or I should say the steady state version of this equation, because our discussion was limited mostly to the critical reactors. Reactor critical means the neutron density is constant and it is producing a constant amount of power. So, the right hand side goes to 0 for a critical reactor, and then we solved this particular equation under steady state for 3 different kind of geometries. We took 3 ideal configuration. The first one is that of an infinite plate, which is having infinite dimensions in 2 coordinate directions and almost 0 in the third coordinate direction, or you can think this one to be a plate with infinite area, but near 0 thickness. And this is a source of neutron which is immersed into an infinite extent of medium, where there is no fission nuclei present. So, the only mechanism the neutron can have are the diffusion and absorptions, and accordingly we got this particular distribution of neutron. Here S double prime represents the neutron emitted by the source per unit area, D is the diffusion coefficient, and L is the diffusion length. If you remember, L square was related to D and sigma A. Then we went to the second condition, where we had a point source of neutron. This being point source, it is capable of emitting neutrons in all possible directions over a sphere. So, we use the spherical coordinate system and got this particular distribution of neutron flux. Here S represents the source strength, that is number of neutrons emitted per unit time by this point source. And the final configuration was again of a line which is infinite in terms of its length, and so it can emit radiation in all possible directions like a cylinder, and using cylindrical coordinate system, accordingly we got this expression where S prime represents the source strength per unit length of the source, and K naught comes from the Bessel functions, or it is the modified Bessel function of second kind. So, for all these three distribution, one thing is common, that at the, which is quite logical as well, near the source the strength of neutron flux is the highest, and as we are moving away from this, that exponentially decreases. But all these three conditions, all being ideal geometries, that was done in non-multiplying media. That means, the neutron source was assumed to be immersed into a media where there was no source of neutron present or no fission going on. Only mechanism is the diffusion, or only mechanisms are the diffusion and absorption, and presence of source was recognized only very close to its close to the center of the coordinate system, or physically where it is located, which provides one of the boundary conditions in calculating these expressions. But practically in a reactor, we can have different kinds of multiplying media present, or I should say it is not only non-multiplying media, rather fuel itself also will be present, so that the neutrons can participate in fission reaction and accordingly produce some new neutrons. So, we can have additional source of neutrons anywhere in the reactor, which accordingly we discussed about the neutron diffusion in multiplying medium, and we got this expression where we have only one additional term. This is only for a critical reactor. So, we are taking 0 on the right hand side, and we are having this additional term here, which represents the generation of neutron because fission. Here nu is the number of neutrons, average number of neutrons produced for fission, sigma f is the macroscopic fission cross section, and phi of course is the distribution of neutron or neutron flux distribution. Now, before and finally, we have discussed about this concept of extrapolated length. Of course, we solve this diffusion in multiplying media for one consideration of infinite slab, and the condition of extrapolated length was mentioned while we are considering the neutron flux to go to 0 at the edge of the geometry. Practical cases generally it does not become 0 there, rather it can continue to proceed in the downstream medium. So, by considering extrapolated length refers to if the medium is allowed to continue, then where the neutron flux approaches 0. So, for most of the cases extrapolated length can be quite small, but when that is a significant portion, then we must add, like if we talk about say if we talk about any particular of these reactions, always which we shall be discussing shortly also, this extrapolated length should provide some kind of correction to the physical length scale to consider. But one point I would like to mention before I move any further, why we are having so much discussion about this neutron flux. Just think about how can you calculate the amount of energy produced in a reactor because of fission. Of course, if E represents the amount of energy released from a single fission reaction, then total amount of energy produced in a reactor should be equal to this E multiplied by the number of interactions. Now, how can we get the number of interactions? Number of interactions as per the definition has to be equal to the macroscopic fission cross section into the phi. So, this should be the number of interaction happening per unit volume, because phi represents the neutron flux, or it is the number of neutrons per unit area, and sigma f is the macroscopic cross section. So, these two together has a dimension of per unit volume, and now we need to multiply this one with the volume of the reactor itself, or we may integrate this one over the entire volume of the reactor. So, that should give you the power produced by the reactor or amount of energy released by the reactor. Now, look at this expression here, this the first term, that this E is the amount of energy released from a single fission reaction. Do you remember how to calculate this? We have discussed this one in the second module itself. Once we know the details of the reaction, then we can always calculate this E very easily, because we just need to know the atomic mass of the parent nucleus and also the mass of the fission products, and then we can calculate a mass balance to identify the value of mass defect, and we know that 1 AMU of mass defect is equivalent to 931 MeV of energy. So, accordingly the mass defect is directly going to give you the value of this E, that is the amount of energy released or amount of mass that got converted to energy through the fission reaction. For uranium or plutonium fission, this E is commonly around 200 MeV or maybe just slightly higher, like quite often a value of 212 MeV is considered. Next, the next term is this after we are able to calculate the value of E, next term was sigma f. Now, sigma f is something that is quite standard, means sigma f as per the definition, capital sigma or sigma f is equal to the nuclear density into sorry, I should write correctly, the nuclear density into, I am repeatedly writing wrong thing, sorry. So, it can be as the nuclear density multiplied by the microscopic cross section. Now, for most of the materials which are used in a common nuclear reactor, the value of this microscopic cross section, microscopic friction cross section or any other microscopic cross section is quite standard. So, we can calculate the value of this macroscopic cross section quite easily once we have idea about this nuclear density. If you think about any reactor, later on in one of the later modules we shall be discussing in details, but commonly reactors can be of two types, one is homogeneous, other is heterogeneous. In a homogeneous reactor, we generally find a homogeneous mixture of whatever component that you would like to put. Just you can think about one of the numerical problems we solved in the previous module. Say your fuel is something like a compound of uranium, like uranyl sulfate or uranyl carbonate kind of thing, which is dissolved into water, and we put this mixture inside the reactor. Now, the uranium 235 that can be present inside the compound acts as the fuel, other components remains as it is, and the water that act as the moderator. So, everywhere as there is a homogeneous composition, the value of these cross sections also remain the same, and in that kind of situations we know how to calculate the cross section, like there the macroscopic cross section or say the average microscopic cross section for the entire mixture will be the not microscopic, I should say the average macroscopic cross section for this should be equal to the n sigma f product for all divided by total n, or I should say the n sigma f product you have to calculate for all components and then sum them up to get the numerator and then divide by the total number of nuclei that is present inside the reactor at that instant of time. Now, once we have calculated this E and sigma f, then we are left with only phi. So, the calculation procedure of both E and sigma f are quite standard, and in that case the entire evaluation of this power that reduces to this phi only, and depending upon the distribution of phi we can have different values of this P in different parts of the reactor, and hence it is of utmost importance to get a perfect idea about the distribution of this neutron flask. So, now we go back to the problem that we have solved during the previous lecture only. Here geometry is of an infinite slab, or reactor is of the geometry of an infinite slab which is having a thickness of A, and the coordinate direction was taken to the center line. So, we solved this and we got this particular form where A naught is the coefficient and which can be calculated from the power rating for this. Here one thing I should mention, while P dot I am using here, this one I am talking about, this P dot refers as power because this is the common symbol that is used, but actually it is more like an energy flask, because this P dot has an SI unit of energy released per unit area of the reactor, watt or kilowatt whatever. So, this while the symbol P dot represents or it looks like energy or power I should say, but actually it is energy released per unit area of the slab. So, we have already done this calculation, and here the buckling parameter that can be calculated as this pi by a whole square because B was found to be pi by a. So, this up to this part we have already done in the previous lecture. Let us now calculate a few more things from here. If we this of course is a cosine distribution, and hence we can expect it to vary along the length of this slab reactor, and hence to identify the maxima it is a quite straightforward procedure. We have to get d phi dx and equate that to 0, and then we get this particular form, and finally get x bar equal to 0, where x bar represents the location of this maxima. So, we can clearly see that the maxima in this neutron flux is located at the center line itself. and hence the phi max can be by putting x equal to 0 in this particular equation, cos 0 becomes equal to 1, and hence we get phi max equal to a naught or whatever expanded form that we have for a naught. And therefore, the distribution phi can be written as phi max into cos pi x by a, because the entire coefficient is equal to the maximum value of this flask. But quite this is the distribution that we can have. It is mirror image with respect to the center line, with a maxima at the center line and gradually decreasing to 0 at the edge. Now, this is the edge, but in this drawing it actually is non-zero at the edge and it is expanded to become 0 at somewhere here. So, this particular portion is the extrapolated length that I talked about earlier. Whenever we have this extrapolated length to be significant, then this A needs to be corrected, or this A needs to be replaced by A plus D, where D is the this extrapolated length or the thickness of the corresponding layer. Also, along with the maxima, quite often an average neutron flux is an important information. As we can clearly see from this picture that the flask is maximum at the center line and sharply reduces to become nearly 0 at the edge. So, now, an average flask can be defined as something like this, which where this phi average should be such a value that it is able to maintain the same power rating of the reactor. Now, this particular one is the total amount of power produced during the reactor, which we have already used earlier, and this should be equal to E sigma f A into phi average, that where E is the amount of energy released, again sigma f is the macroscopic fission cross section and A is the thickness of this slab reactor or half width of the slab reactor. And hence, we finally get this particular expression. This average phi value can be calculated as 1 by A into integral of phi x dx over the entire reactor, that is minus A by 2 to plus A by 2. It comes out to be 2 by pi into phi max. So, quite often to understand the non-uniformity that can be present inside the reactor in terms of neutron flux, we define a peaking factor. This peaking factor is defined as a ratio of the maximum flask and the average flask, and in this case it is clear the maximum flask is about 1.57 times greater than the average flask. So, that is a strong indicator of the asymmetry that can be present inside the reactor in such a configuration of infinite slab. Now, but infinite slab reactor is only an idealization, because nothing can be infinite in terms of length, and hence we need to go to a more of a finite geometry. While there are quite a few finite geometries, but we have selected the spherical reactor as for our consideration. The governing equation remains the same, that is Laplacian of phi plus b square phi is equal to 0, b being the parameter, the buckling parameter. For critical reactor, we know that bg square and bm square has to be equal, and which is given by b square. So, this is a spherical reactor, and hence we have to use the spherical coordinate system, which gives like this. If we assume the entire phenomenon to be isotropic in nature, then only variation that remains is in the radial direction. So, accordingly this is the equation that we are having, and after solving this, again a very standard ODE. So, after solving this, we have A1 by r into sin br plus A2 by r into cos br. Now, we have to find the value of these two coefficients A1 and A2, for which we need to know the boundary conditions. What can be the common boundary conditions? One boundary condition can be the value of this flask at the edge of the reactor, that is at r equal to capital R, and other condition, suppose if we put in this equation r equal to 0, means we are talking about the center line. Center line r equal to 0 would lead to the if we focus on this term, this gives to a 0 by 0 kind of form in that situation, which is completely impracticable, and hence only realistic solution that we can get from this set of equation is when this A2 goes to 0. A2 has to goes to 0, otherwise the neutron flux becomes infinite at the center line. So, we now are left with only a single coefficient, which is A1, which we have to find very shortly. Now, this is the other boundary condition, that is at the edge of the cylinder, or not cylinder, edge of the spherical reactor, is R equal to capital R, we have the condition of phi equal to 0. If we are having some kind of extrapolated length, like shown in the diagram, this portion is the extrapolated length in the diagram. This R equal to capital R condition, that we have to impose on the same equation, and we can find that at phi equal to 0, or phi equal to 0, R equal to R, we have A1 by R into sin BR, and hence as A1 and R both are non-zero numbers, so sin 0 has to come out. Sin 0 we know that that is equal to possible only when it is equal to n pi. So, accordingly BR becomes to n pi, where n is any integer, and hence Bn is equal to n pi upon R. N can be any integer from 0, 1, 2, etc. Now, as we have used in the previous exercise also, here while there are theoretically several modes of operation, but nothing beyond the 2 or 3 that works. So, Bn equal to n pi by R, where n is equal to any integer starting from 0 going to 1, 2, etc. But as we have seen in the previous exercise also, here while there are several possible modes, but all the modes for which n is greater than 1, they subside quite quickly, and leaving the final profile to resemble only the profile corresponding to n equal to 1. Of course, n equal to 0 is not possible, because if we put n equal to 0, that will give phi equal to 0, and hence your n equal to 1 is the most realistic solution that we can have of this particular form, A1 by R into sin pi small r by capital R. And total power produced, in order to get the value of A1, we have to use the total power produced by the reactor, which is again given by a form like this. Here E is the amount of energy produced by each fission reaction, sigma f is the fission cross section, phi is the neutron flask which we have just derived, and dV is the volume change. It is the volume over which we are doing this entire integration, or volume of the reactor. Basically, we are doing this integration over the entire volume. So, it reduces to a form like this, and finally, we get the form of phi as something like this, a sinusoidal profile, which is having its maxima at the center line, and it is 0 at the edge, that is when small r becomes equal to capital R, it is equal to 0. But following the same pattern, we can also calculate the maxima of this flask and its location, and also the average value of this flask. And for any other geometry also, you can keep on repeating the same exercise, but that will be too much cumbersome to do, and hence I have summarized these results of quite a few other geometries in this particular table. For the infinite slab and for the finite cylinder, we have already developed. This is the infinite slab for which we have developed. For finite cylinder, we have, or not finite cylinder, actually for the spherical reactor, we have just now touched upon. And we can have all the geometries like a cylindrical reactor, we can have a rectangular parallelepiped type reactor. For each of them, we can repeat the same procedure by following the proper coordinate system. Like if you are dealing with the rectangular parallelepiped, then variation is there in all three possible directions, and hence we need to adopt a 3D method or 3-dimensional approach to identify the flux profile there. Same for an infinite cylinder or even a finite cylinder. If we know the values of R and H, still we need to put the assumption of axisymmetricity, and then only we shall be able to analyze this finite cylinder following a 2-dimensional cylindrical coordinate method. But the most interesting factor here is the last column, which is the peaking power. Here we can clearly see all these values are much greater than 1. I am just going back to the previous slide. Here we can clearly see, or in case of infinite slab also that was true, the neutron flask is very high at the center line and then diminishing very sharply and approaching 0 close to the edge. That is because of a large difference between the maximum and average value of this neutron flask. 1.57 was the value for infinite slab which we have derived already, but the same number for the finite sphere comes to be greater than 3 and for other several geometries as well. Now, this is not at all desirable, because inside the reactor we would always like to have a flat profile of the neutron, so that the rate of reaction remains more or less the same in every part of the reactor. If the neutron flask is high only at the center line and very low or 0 at the wall, then the fluid which is getting energy close to the center line will become superheated very quickly, whereas the fluid which is closer to the center may not get that much of energy, or rather the power production there remains 0. So, while the coolant goes out of the reactor channel, there will be a large amount of axial variation in temperature, and that can cause lots of several other issues. Hence, we must ensure that the neutron flux profile remains more or less flat. While the infinite slab 1.57 is quite an encouraging number, but it is still a concept only. So, we must ensure that the neutron flux remains flat, and so that we can have a uniform distribution of energy received by the coolant over the entire cross section. And one way of achieving that is by the use of reflectors. If you can remember earlier that the reflector, we have mentioned in one of the earlier discussions that the reflectors are commonly used to reduce the neutron leakage from the reactor. Now, neutron going out of the reactor is never desirable, rather because that reduces the neutron density inside the reactor and thereby affects the power generation inside the reactor. But use of reflectors can reflect some. Reflectors are materials which are having higher scattering cross section, and so they can reflect or diffuse some medium back into the reactor, and hence it can provide a reduction in the total mass or the critical mass of the reactor. But it was mentioned earlier, it can also provide a more uniform neutron distribution, and here we can see how that can be done. So, typical reflectors can have both kinds of designs. It can have axial reflectors or radial reflectors. This is axial reflector, where reflectors are used only at the inlet and outlet section of the channel, whereas this is radial reflector, where reflector is there all around. Both of them have their own pros and cons, but generally the radial one is found to be more convenient, also much easier to design, and therefore the radial reflector is more commonly used, particularly in common pressurized water reactor or boiling water reactor. The reflector, radial kind of reflector is preferred. It is also very common to have the entire core of a boiling water reactor to get immersed into a pool of water, because water is a good reflector. Now, we assume a slab type reactor of width A and is surrounded on both sides by a non-multiplying reactor slab of thickness B. Like the geometry of slab which we are taking earlier, this is the slab type reactor where thickness is A, or you can say at each of the side it is A by 2, but this is the additional part. Now, we are having this reflector of thickness B on both sides of this slab. So, we have to analyze this thing, and while the analysis for such a geometry we have already done for infinite slab, but the reflector was not there. So, for the reactor core we can write the conservation equation to be like this, just the same form, the diffusion part, the absorption part and the generation part because of fission, but this equation is applicable for x equal to 0 to a by 2. Here the mod x is written because diffusion can be equal in both the positive and negative coordinate directions, and so we are taking mod of x. Here the subscript c that has been used, that refers to the core. So, phi c refers to the distribution of neutron flux inside the core. So, this equation being standard, we get this solution. One of the coefficient, as was mentioned earlier, in order to keep the neutron flux finite at the center line, the sinusoidal term goes out, we are having only the cos term that is remaining. Now, for the reflector, that is from a by 2 to a by 2 plus b, within that this is the corresponding conservation equation. Here phi r is the neutron flux inside the reflector, there is no multiplication or no fission going on, so we do not have a third term, but we definitely have the other two terms, that is the diffusion of neutron inside the reflector and also the absorption of neutron. Now, if we solve this one, we are going to get this particular form of solution for phi r. Again boundary condition has been applied and one of the coefficient goes off, leaving only one coefficient. So, this A1 and A2 are the two coefficients that we need to solve using the power rating of the reactor and any such information. Now, what we should use as the boundary condition to get these values of this, the value to get a coupling between these two. Of course, the reflector, you have to understand that the reflector, if I draw the diagram again, this is the center line, this is the edge of the core and this is the reflector. Now, in the reflector there is no source of neutron because there is no fission going on. Then from where it can get the neutrons? That is only possible by diffusion from the core itself. And as there is a diffusion going on, as there is a strong transfer of moment neutron is going on from the fuel to the reflector, this particular interface is of very large importance. This is corresponding condition is called interface boundary condition. Interface boundary condition ensures that flux phi does not have any kind of discontinuity or jump at the interface, rather the value of flux neutron flux distribution in the core and the same for the core distribution at inside the reflector, they should be equal at this particular interfacial surface. If then only we can avoid any kind of jump in the value of the neutron flux. And we have a second boundary condition. The equality of flux alone is not sufficient, rather we also have to consider the gradient of the flux or the neutron current density. That also should be equal for both core and reflector at that interface. So, here J represents the neutron flux density or neutron current density, and by using the fixed law of diffusion we arrive at this, J being d of d phi dx. So, we get this particular equation. So, accordingly we have two expressions where we are taking the equality of neutron flux between reactor and core, and this is another one where we have the gradient of velocity at reactor and also at the reactor core and also at the reflector. If we combine these two boundary conditions, then this is solution that we are going to get. Now, if combining these two, this is the final form of the equation that we are getting. I have skipped the intermediate steps just to save some time. Here BGC refers to the buckling parameter for the core, DC and DR are the diffusion coefficients for the core and reflectors respectively, and LR refers to the diffusion length inside the reactor, inside the reflector rather. For this reactor to be critical, this above equation must be satisfied. Now, this is actually a transcendental equation, and so we can't solve it directly, rather it requires iterative solutions with some possible starting guess. This can be used to calculate either this buckling parameter B or any other parameter, so is a dimension A. That depends on what information is made available to you, we can decide which one to calculate from here. Like if your objective is to identify the dimension of this reactor, then you definitely try to solve this for A with a knowledge of this buckling parameter. Similarly, if the objective is to identify the buckling parameter, then we need to know the information about the A. This is the kind of profile that we are going to get. The first one, that is this one, is unreflected. There is no reflector there, and we can see the rapid decline in the neutron flux distribution. But once we put the reflector in, look at what we are having. Now, this is the corresponding flux distribution, and they are definitely much flatter and reaching 0 only at the edge of the moderator. So, use of reflector definitely helps in flattening out the neutron flux distribution, and hence it can lead to a higher rate of fission reaction and even also neutron flux distribution, and thereby allow a smooth distribution of temperature. Next, if we do the same exercise, it was done for an infinite slab reactor, which is a bit of idealization. if you do it for a cylindrical reactor, and then we are going to get this kind of relation. Another transcendental equation here, R refers to the diameter of the cylinder, or rather radius of the cylinder. And for the special case, when both the moderator or the reflector and the core are having identical values of the diffusion coefficient, or basically when the same medium is used at the moderator and in the reflector in the reactor, then this ratio of dc by dr by dc that goes to 1, and it reduces to a even simpler form. And now this does not seem to be a transcendental one anymore, because not special for simplified, we get this particular simplified form, BGC equal to cot of R BGC to 1 by LR. This is not transcendental, because if the value of BGC is given, this can be used to calculate the radius of the cylinder. The magnitude of the coefficients I have already mentioned. These two coefficients A1 and A2 can be calculated from the power rating of the reactor. And finally, we have the two group approach to talk about. So far, whatever analysis we have done, there we have considered a single group of neutrons, because we are dealing with one group diffusion equation or one group Newton diffusion equation. But during a nuclear reactor, neutron goes through different levels of energy. Like initially the neutrons, when they appear because of fission, they are fast in nature, then they pass through the moderator and becomes intermediate temperature level, and when at the intermediate temperature zone, it can get eaten up, or the resonance absorption that happens, and so it is able to reach the thermal neutron level. Accordingly, we can have a very wide spectrum of neutrons present in the reactor. This is one of the representative diagrams. Here this purple color line represents thermal reactors, or thermal the neutrons produced because of thermal fission. The red one represents that for fast fission, and you can clearly see there is a wide spectrum of energy with which the neutron can appear. So it is more logical, instead of using a single group assumption, it is more logical to lump the neutrons into several energy groups during the analysis. There are several ways they are clumped. Sometimes people prefer 3 groups, like the first neutron group, the intermediate neutron group, and also the thermal neutron group. But here we shall be sticking ourselves to the 2 groups to show an example, where are fast neutron and thermal neutrons. So once that is in the level of fast neutrons, that is kinetic energy is of the order of 1 MeV, then we shall be taking that into the fast neutron group, or we shall be considering that in the first neutron group, and whenever the energy is less than that, we shall be considering that in the thermal neutron group. And the properties of each group are averaged over the constant range of energy. Like these are some numbers which are generally considered for the thermal group neutrons, and they also depends upon the moderator. So the first one is the absorption cross section, second one is just the reciprocal of that, which is the absorption mean free path. Then we have the diffusion coefficient, and finally the diffusion length L. L is again d by sigma A, so from there also it can be calculated, or L square is d by sigma A, so from there L can be calculated. So these are the most common 4 moderators, and you can clearly see the H2O is having a quite small diffusion coefficient, but there are other mediums. They are like D2O. D2O has a much larger diffusion coefficient, quite close to graphite, and its diffusion length is also much larger. And these are corresponding numbers for fast neutron groups. Again, here the graphite or carbon is the one that is showing very large values of this diffusion length. Now we have to present a very brief mathematical analysis. So we are assuming that the neutrons appear in the first group as a result of thermal fission only. That is, when the thermal neutrons participate in fission reaction, the products of those are the one that comprises this or constitutes this first group. But the only source of thermal neutron is when this first neutrons passes through the resonance absorption zone, and because of the scattering it becomes thermalized. So for a critical reactor we can write 2 different equations, 2 different balance equations. This is for the first group of reactor, which you can think about the first reactor group, Here we have the first term is the diffusion of first reactors, then absorption of first reactor, because of which the number of neutrons will decrease, and third is the production of first reactors. Of course, K infinity gives you the total multiplication factor, the infinite multiplication factor, and once we are dividing that with the resonance escape probability, this is the rate that we are going to get. Similarly, for the second group, this is the equation where along with the leakage and absorption term, we have this, it represents the amount of neutrons, that is the source of neutrons, which is the neutrons which are passing through the resonance absorption zone, and hence P is the resonance escape probability. So, sigma A 1 multiplied by this P is the amount of neutrons that are able to thermalize, and hence be part of this thermal neutron group. Now, both kind of fluxes generally show the same kind of spatial dependence, and hence they have an identical geometrical buckling. Accordingly, the first equation takes this particular form. Here we have only represents that Laplacian of phi as the buckling into phi, or minus of that rather, or you can also write this as this plus this is equal to 0, an equation which we have repeatedly used. So, with that substitutions we get a form like this, and we can do a similar procedure for the second one. This is the corresponding equation. So, we are having basically two algebraic equations which are coupled with each other, and the solution of non-zero or non-trivial solution for this is possible only when this particular determinant of the coefficients is equal to 0. So, from there we get this as the final solution. This equation has to be satisfied for a reactor to be critical, a reactor with reflector to be critical. Here the denominator can also be viewed in this way, like 1 by L1 square Bg square can be thought about the first neutron non leakage probability, whereas the second term or the reciprocal of 1 plus L2 square Bg square can be viewed as the thermal neutron non leakage probability. So, instead of P1 we can also write this as Pf, and we can also write this as Pth. These are the two non leakage probabilities, because that includes the diffusion length as well, diffusion length for the zone 1 and diffusion length for zone 2. So, this way we can analyze these two different groups of neutrons. There can be situations where you have to deal with more than two number of groups, and just by putting these equations, writing corresponding equations for each of them and applying suitable boundary conditions, and so also coupling situations, you can always solve this kind of systems. So, that takes us towards the end of this fourth module, where we have discussed in detail about the chain reaction, and we have understood that it is absolutely essential for sustained power generation in nuclear reactors. Then a critical reactor is characterized by a multiplication factor value of 1 and reactivity of 0. The diffusion of neutron in a medium is roughly governed by the Fick's law. Using the Fick's law and also neutron balance, we have written the single group neutron diffusion equation, which includes the diffusion term, the neutron production because of fission or external source term, and we can also have the absorption term. Then following from there onwards, we have identified that the critical reactor must ensure identical magnitudes of both geometrical and material buckling parameters, because that is the mandatory condition. Or we can also write mathematically Bg square is equal to Bm square. The distance travelled by the neutron inside a reactor can be related to the diffusion length. There we have also distinguished or differentiated between the diffusion length and the mean free path. Mean free path is the total distance travelled by a neutron between two successive interactions, whereas the diffusion length is the straight line distance from the point of its birth till the point where it gets absorbed. Then we have done the mathematical analysis of the Bayer reactor, and we have seen that a Bayer reactor shows large deviation in the value of the neutron flux distribution, with the maximum at the central line and the 0 at the edges, or in some cases if the extrapolated length is considered, is 0 at the extrapolated length. and then we have analyzed with the reflectors, and it was find that use of reflectors can lead to more significant flux distribution and hence offers a lower critical max. So, this is the fourth module where we have discussed about chain reaction, and now you have much clearer idea about the possible neutron flux distribution that we may encounter in a particular reactor. And once we know or once we have the complete information about this flux distribution, how to utilize this in calculating the power rating of the reactor. So, this is the end of okay, actually I forgot about mentioning the last one, which is the two group approach, which was found to provide a more realistic estimate and but added computational or mathematical complexities of course. So, we now know how to calculate the total energy that can be produced from a reactor, and in the next module we shall be discussing about how we can harness that energy and transfer that to the coolant, because we shall be talking about the nuclear thermal hydraulics. So, just wait for that, and for the moment thank you and bye.